Hi everyone. Today we are going to discuss about orthogonality of vectors in an inner product space. So let us start with a motivation. Let us take that x equal to x1 comma x2, y equal to y1 comma y2 in R2 minus 0 0. Two non-zero vectors. We know that the scalar product of xy or dot product of xy is nothing but x1 y1 plus x2 y2, and that is nothing but Euclidean norm of x2, Euclidean norm of x multiplied by Euclidean norm of y multiplied by cosine theta, where theta is between 0 to 2 pi. We know that if theta equal to pi by 2, this dot product of x with y or inner product of x with y is 0, and we know that when the angle between two vectors is pi by 2, we call them as orthogonal vectors or perpendicular vectors. So this implies x and y are orthogonal. Each other. Now based on this concept, we define orthogonality in an inner product space. Let us take, let x be an inner product space and x y are coming from x. Then we say that x is orthogonal to y. If inner product x with y is 0. The notation is the following. We denote this by writing x is orthogonal to y and x is perpendicular to y. Okay. Now what is the advantage of having orthogonal vectors? So immediate observation is that if x is orthogonal to y, then we can look at x plus y norm square. By expanding using the inner product, we can easily show that this is norm x square plus norm y square, because inner product x with y is 0. Now this is exactly the generalization of the Pythagorean property that we learn from the Euclidean geometry. So this is called Pythagorean property. Since this Pythagorean property is valid for two vectors, we can say that it is also valid for finitely many vectors. So let us take x1, x2, so on, xn in x, such that xi is orthogonal to xj for ij in 1, 2, 3, so on, n, and I not equal to j. Then we can say that norm of x1 plus x2 plus so on plus xn square is nothing but norm x1 square plus norm x2 square, so on, norm xn square. So this is the Pythagorean property for n vectors which are mutually orthogonal to each other. Okay, this orthogonality concept we can even define for any subset of an inner product space. So let us take S be a subset of x. Then we define S per or orthogonal complement of S in x as follows: set of all x in x such that inner product of x with y is 0 for every y in S. That means all those vectors x in x which are orthogonal to every vector in S. So that means X is in S per if and only if X is orthogonal to Y for every Y in S. Okay. Now using this definition we can obtain a few important properties. So we started with S to be a subset of X. We don't know whether it's a subspace or not, but we can always show that S perp is always a closed subspace of X. This we can show by using the continuity of inner product in both variables. The second one is, if you take S perp and this again perp, this is nothing but, this we usually write as double perp, is nothing but span closure of the set S. That means that is closure of span of S, that is the smallest closed subspace containing S. Containing S. The third condition is, if S1 is subset of S2, then we can say that S2 perp is contained in S1 perp. The inclusions get reversed. The fourth property, if you take 0 and take orthogonal complement of 0 in X, that is the full space X, and orthogonal complement of X in X itself is nothing but the 0 space. So these results can be proved very easily. Okay, so this is about orthogonal complement of a set in a inner product space. For example, if you look at a simple example, let us take X to be R2 over the field R. Now let us take S as X comma 0, where X is coming from R. This is the x-axis. You can show that S perp is nothing but the y-axis. This can be shown very easily. Okay. Next we discuss about orthogonal set and orthonormal set. So a set S of X, where X is an inner product space, is said to be orthogonal if inner product X with Y is 0 for every xy in S and X not equal to Y. If you take any pair of elements from S which are distinct, they should be mutually orthogonal. We say it to be orthonormal if S is orthogonal and norm of X equal to 1 for every X in S. It's an orthogonal set containing unit vectors. Let us see a few examples and the importance of this orthogonal and orthonormal sets. Let us take X to be C power n. Here field is C. We take E1 as 1, 0, 0 so on, e2 as 0 1 0, and in general ek en 0 0 so on 1. So if you take s as e1 e2 so on en, let us take s to be the set, then s is orthonormal. Let us look at one more example. Let us take x to be the C00 space which we have defined earlier. You know that this is subset of L to N, and the inner product on C00 is the inner product coming from L to N. Now let us take E1 as 1 0 0, E2 as 0 1 0 so on. In general En is 0 0 1 0 0, and this is the nth place. So on. Then we can say that this set E1 E2 E3 so on is an orthonormal set. In C00 and hence in L2 of n. Okay, so here I have taken this to be x. Okay, let us look at one more example. Let us take x to be c of minus pi to pi, the set of all continuous functions defined on the closed interval minus pi comma pi, taking values in c, and f is continuous on minus pi comma pi. For fg in x, we have defined inner product f with g as interval minus pi to pi, f of t gt bar dt, and we know what is the induced norm also. Now if you look at this set, 1 by root 2 pi cos nt by root pi sin nt by root pi, where n is a natural number, is an orthonormal set. In X. In particular, this is also orthonormal set in L2 also, L2 of minus pi comma pi. Okay. So one more important observation about orthonormal set in general is that it is linearly independent. So let me write as a remark. An orthonormal set in an inner product space is linearly independent. Okay. Now we can ask the question, is the converse true? In general, this converse is not true, but actually we can find an orthonormal set from a linearly independent set. So this process is known as the Gram-Schmidt process. It says that suppose x1, x2, so on is a linearly independent set in an inner product space. Then there exists an orthonormal set it is called En in X such that if you take span of x1, x2, so on xn, span of x1, x2, so on xn is span of e1, e2, so on en, where n is in n. That means you can take span of x1, you will get span of e1, span of x1, x2, you will get span of e1, e2, so on. So this is the Gram-Schmidt process. Let us try to look at the idea how to construct such vectors. First, what we do is, let us write y1 as x1 by y1 is x1, and you take e1 as y1 by norm yy. We can explain this geometrically in order to take a vector x1 and take another vector x2. So this is the unit circle. Now normalize this vector x1, that is x1 by norm x1 is the vector e1 here. Now you can extend this vector lambda e1 so that this is orthogonal to x2. So lambda, this vector is lambda e1, so x2 minus lambda e1 is orthogonal to e1. So now using this we can actually find out that if you take y2 as x2 minus x2 e1 inner product multiplied by e1, then you take e2 as y2 by norm y2, so that it becomes a unit vector. So proceeding this way, actually we can write yk as xk minus summation j equal to 1 to k minus 1 inner product with xk ej and ek as yk divided by norm yk, so that it becomes a unit vector. Now if you look at from the beginning, that span of y1, span of x1 is e1, span of e1, span of x1, x2 equal to span of e1, v2. So in this way we can actually get the result that we want. So this is the way we can construct orthonormal set from a linearly independent set. Okay, now let us look at some more important properties of orthonormal sets. Let us take x1, x2, so on be an orthonormal set in an inner product space X with this inner product, and take X from X. Then if you look at X minus summation j equal to 1 to n inner product X xj multiplied by xj norm square. If you compute this one, you will get norm x square minus summation j equal to 1 to n modulus of inner product x with xj square. we know that this is always positive. So from this we can conclude that summation j equal to 1 to n modulus of inner product x with xj square is less than or equal to norm x square. Okay, now this is for any n. So from this we can conclude that summation j equal to 1 to infinity mod x xj square inner product of x with xj and mod square less than or equal to norm x square. Because in the above step the nth partial sum sequence of this series contains only positive terms and it is increasing and bounded above by norm x square, hence it must be convergent and the limit is nothing but this series. Okay, this inequality is well known as the Bessel's inequality. That means the series on the left hand side is convergent. It's also from this we can conclude that immediate remark inner product, if you look at inner product x with xj, this converges to 0 as j going to infinity. Okay. There is another way of expressing the Bessel's inequality using a family of vectors. Instead of taking countable vectors, we can take uncountable also. Let us look at that part. Let x alpha is in some index set I be a family of vectors in an inner product x with this inner product. Then we say that this family is summable to x in x if for any epsilon positive there exists a finite set j naught of I such that norm of x minus summation over alpha in j x alpha norm less than epsilon for every finite subset j of I containing j naught. If you take the index set I to be the set of all natural numbers, so this is exactly the convergence of the series to the element x. So this is a generalization of series convergence. Now using this we can actually show that Bessel's inequality is true even if you replace countable family by arbitrary family of orthonormal sets, orthonormal vectors. Let x alpha be a family of orthonormal vectors in an inner product space x with this inner product. Then we can say that summation alpha in I modulus of inner product x with x alpha square less than or equal to norm x square is true for any x. So this is again known as the Bessel's inequality. This can be proved using the earlier result and the definition of summability of family of vectors. Okay. Next we can ask the question that given any orthonormal set, how to get an orthonormal basis out of that. So before that, let us discuss what is an orthonormal basis. A maximal orthonormal set in a Hilbert space is called an orthonormal basis for the Hilbert space. We know that every Hilbert space has a basis, and using the Gram-Schmidt process we can convert a linearly independent set into an orthonormal set. Now using the Jones lemma we can get that every Hilbert space has a orthonormal basis. So every Hilbert space has an orthonormal basis. For example, you take x to be c power n and the field is C. If you take E1, E2, so on En that we have defined earlier, you can easily show that this is an orthonormal basis. For c power n or for x. Okay. Now the question is, given any orthonormal set, how to get orthonormal basis out of that, or when we can say that given orthonormal set is an orthonormal basis in a Hilbert space. So this can be given by the following result theorem. So we will not prove this theorem, but this is very significant in the sense that we can actually give equivalent conditions for an orthonormal set to be an orthonormal basis. So using any of those conditions we can actually say that when an orthonormal set is an orthonormal basis, that x alpha coming from I be an orthonormal set Hilbert space H, then the following are equivalent. The first one is x alpha is an orthonormal basis if you take inner product of vector x with x alpha, and if this is 0 for every alpha in I, you can say that x must be 0. So usually we know that if x is orthogonal to every vector in the inner product space or Hilbert space, that vector must be 0. Here when x is orthogonal to every element of the orthonormal basis, then x must be 0. The third condition says that x can be written as summation alpha in I inner product x with x alpha multiplied by x alpha. So that means we can express x using this series. This series is known as Fourier series of x. the fourth equivalent condition is by looking at the norm of x. Look at norm of x square. This is nothing but summation over alpha in I modulus of inner product x with x alpha square. This is known as Parseval's identity. And the last one is, if y is another element of H, then we can say that inner product x with y can be written as summation over alpha in I inner product x with x alpha multiplied by inner product y with x alpha bar. Again, here the meaning of series is as explained in the earlier discussion, that the summability of a family of elements. So this is the same meaning here, but actually using the Bessel's inequality, we can actually show that as a consequence of Bessel's inequality, we can show that if you look at this set of all E alpha such that inner product x with E alpha is non-zero, so per x in x, so this is a countable set. This comes directly from the Bessel's inequality. This can be proved easily. Now once that is countable set, and if you look at equivalent statement 3 and 4, the series contains only countably many non-zero terms, remaining terms are 0, so we can actually replace by the series by countable series, a series with countable terms, even in 3, 4 and 5. Okay, so these are the equivalent statements for an orthonormal set to be an orthonormal basis. By looking at these conditions, we can actually determine whether a given orthonormal set is orthonormal basis or not. Let us look at a few examples. We can show that if you define En at M, or we can define like earlier, En equal to 0, 0, 1 in the nth place, remaining 0. We can show that this En is an orthonormal basis for the space L2 of N. Similarly, we can show that whatever the orthonormal set we have given for C of minus pi to pi, we can show that this set is orthonormal basis for L2 of minus pi to pi. So these are a few important properties of orthonormal sets and orthonormal basis.